It started as a faint blur, an icy speck drifting in silence, far beyond the orbit of Mars. Our two Swan, just another comet, unremarkable, forgettable, until it erupted. In the deep vacuum, far from Earth's atmosphere, something inside Swan fractured. The pressure built. Then it blew, not with sound, but with light. Its coma expanded, its tail ignited, and within hours, it became visible to the naked eye. A sudden outburst triggered by internal volatile gases cracking through its crust, releasing frozen secrets forged billions of years ago. And that was just the beginning. Because at the same moment Swan came alive, the sun grew restless.
If you're still watching, subscribe now. You crave more than answers. You seek what lies beyond. Subscribe now and be part of the few who never stop searching.
An M6.4 class solar flare tore through Corona, one of the strongest of the year, unleashing coronal mass ejection at blistering speed. It wasn't earthbound, but it didn't need to be. Its trajectory intersected one thing, the ion tail of Comet Swan. That set the clock ticking. When high-energy solar plasma slams into the magnetic environment of a comet, nothing stays the same. The ion tail, already hundreds of thousands of kilometers long, becomes a target. If the CME's magnetic field opposes Swan's, reconnection happens. Violently. Field lines snap. Plasma breaks free. Tails disconnect. It's rare. It's unpredictable. And it's happening in real time. The CME isn't just a solar storm. It's a scalpel slicing through space, headed straight for a supercharged comet on the verge of instability. The physics? Massive. The scale? Interplanetary. The outcome? Unknown. But Swan isn't alone, racing to the same stretch of space. 3 Eyes/Atlas, an interstellar object, born in another solar system, forged under alien stars. Now aligned with Swan in a cosmic near collision of opportunity. One native, one foreign, both exposed to the same blast wave of solar fury. 2 celestial bodies, one magnetic storm. This is more than a spectacle. It's a laboratory, millions of kilometers wide, built by nature, timed by chance. Scientists call it magnetic reconnection. Plasma physicists call it unrepeatable. Because you can't recreate this in any lab on Earth. The energies are too high. The distances too vast. Amateur astronomers lock in. Observatories around the world calibrate their instruments. Telescopes track the curling tail, watching for disconnection events. Jumps, kinks, sudden severings. The world watches Swan, not for beauty, but for data, because this is more than a comet lighting up. It's a window into how small bodies respond to stellar violence. It's how comets die or evolve. It's how plasma behaves when slammed with magnetic force. And it's how the sun reminds us it doesn't just affect Earth. It shapes everything. Swan isn't falling to Earth, but it's heading towards something even more volatile. A wall of fire, a collision of fields, a cosmic experiment written in radiation. And when it hits, if it hits, the solar system will show its teeth. You're looking up into the October night sky of 2025, and something's different. There, streaking across the dark, is a comet that wasn't supposed to be this bright, wasn't supposed to be this visible. Comet R2 Swan has changed. What began as a faint, mostly forgotten object has erupted, violently, unpredictably, transforming into a naked-eye spectacle that's now racing toward Earth's vicinity with accelerating urgency. This is no ordinary comet flyby. It started quietly. R2 Swan was another distant body in a long list of comets, barely worth a mention, until it wasn't. Then came the outburst, a sudden, dramatic release of energy from deep within its icy core. Its brightness spiked, its coma expanded, its tail stretched longer and wider, threading across the sky in a glowing streak. This wasn't some trick of optics. It was raw celestial activity, an eruption driven from the inside out. The core had cracked open. Volatile gases, sealed for millennia beneath layers of rock and ice, tore their way free under the heat of the sun. They burst out, dragging clouds of dust behind them. The nucleus had fractured. Internal pressure had reached a breaking point. This wasn't a passive object, sublimating as it warmed. This was structural failure on a cosmic scale, and it caught everyone off guard. But the timing is what's turning this into something far more extraordinary. Just as Swan's tail expanded into a vast, delicate veil of ionized gas, the sun unleashed an M6.4 class solar flare. Powerful, complex, accompanied by a coronal mass ejection, a CME that burst from the solar surface at staggering velocity. Billions of tons of plasma hurling through space, magnetically charged and moving fast. Not toward Earth, but right through the sector of space where Comet Swan's tail now drifts. That matters, because what's about to happen next is a high-stakes experiment no one planned, but everyone's watching. When a CME collides with a comet's ion tail, it's not like a gust of wind against a streamer. It's magnetic warfare. The ion tail of a comet is shaped by the solar wind, tuned to the sun's magnetic field. When a CME slams through with a different, possibly opposing magnetic orientation, things start to snap, reconnect, break. This is called magnetic reconnection, and it can tear a comet's tail clean off. It's rare, it's unpredictable, and it's violent. If the CME impacts Swan's tail with the right polarity, you may see it fragment, brighten, kink, or even disconnect entirely, severing the void by invisible forces moving faster than comprehension. This is not theory. It's physics. Plasma physics, played out in real time across millions of kilometers. Magnetic reconnection is one of the most powerful and least understood forces in the cosmos. It's what powers solar flares. It's what lights auroras. It can twist entire magnetospheres and strip them bare. And right now, it may be about to carve through Comet Swan like a blade of pure energy. It's not just the visuals that matter. It's what this means for science. Because reconnection events on this scale are almost impossible to reproduce in terrestrial labs. The temperatures, the distances, the scale, it doesn't translate to Earth-based experiments. But here, in this accidental, real-time cosmic laboratory, we may get to watch it all unfold. Raw data, untouched variables, space plasma behaving under pressure. And that's only one layer of this. Because something else is approaching. Something interstellar. 3I/Atlas, another visitor. Not from the Oort cloud. Not from our system. It's crossing through on trajectory that's brought it startlingly close to the same region of sky. Not close in astronomical terms, but close enough to matter for observation. It's a chance alignment that no one could have planned. Two comets. One born from the solar system. One from the space between stars. Both moving through the influence of the same solar event. It's a comparison that scientists rarely get to make. And it's happening live. Interstellar objects are rare. Before 3I/Atlas, only two had ever been definitively identified, Oumuamua and 2I/Borisov. These bodies carry information not just from another solar system, but from another time, another set of physical conditions entirely. Comparing one to a native solar system object like Swan in the middle of a space weather event is not just interesting, it's groundbreaking. We're talking about two cosmic bodies being shaped in real time by the same external force, under very different internal constraints, and watching how they react, how their tails form, how their brightness changes, how their plasma responds, could tell us more about both of them than years of theoretical modeling. And it's not just the big telescopes watching, because almost overnight, this became a global citizen science event. From observatories to backyards, from professionals to amateurs, everyone is watching, tracking changes in brightness, documenting shifts in the tail, measuring color, shape, and structure. Every image captured by someone on the ground adds another data point, another piece to the puzzle, because comets don't wait. They don't repeat. What's visible tonight may be gone tomorrow, and what Swan is doing can't be predicted. The sudden outburst suggests deep instability. This isn't just surface melting, it's systemic change. The inner nucleus may be breaking apart. Gases trapped for billions of years are erupting into vacuum, and the stress from solar heating, amplified by direct interactions with solar wind, could trigger more outbursts, more fractures, more chaos. And that's before the CME even arrives. If magnetic reconnection happens, If the tail is disrupted, it won't just be a visual phenomenon. It'll be a physical transformation. The whole magnetic environment of the comet could shift. Ion flows might reverse. Radiation pressure could redirect material. We may see brightening, twisting, or fragmentation. The tail might be sliced in half and reformed just kilometers behind, all of it governed by forces we can't touch, but can now, briefly, watch unfold. Every layer of this moment is valuable. The volatile response of Swan gives us a live model of what lies beneath the comet's crust. The impact of the CME shows us how solar storms alter the bodies that pass through their wake. The presence of 3 I/Atlas gives us a control group, another traveler, with a different origin story, responding under the same conditions. For astrophysicists, heliophysicists, and planetary scientists, this is not just a lucky break. It's an event of record, and it's a reminder space is not static. The objects we catalog and classify are not inert relics. They're dynamic, volatile, active. R2 Swan is not behaving like a relic from the formation of the solar system. It's behaving like a live actor in an unfolding cosmic drama. And there are stakes. Solar activity is rising. We are in the early years of solar cycle 25, and M-class flares are becoming more common. Each flare, each CME, has the potential to impact not only comets, but satellites, infrastructure, even Earth's magnetosphere. Understanding how these events interact with different types of objects, solid, icy, interstellar, is essential to understanding the risks they pose. This isn't just spectacle, it's preparation. The data from this event may help refine CME models. It may enhance space weather forecasting. It may reveal new aspects of cometary physics that shift how we approach future missions, whether to study, redirect, or deflect small bodies. And it happened without warning. A dim object brightened. A solar flare erupted. A CME was born. And across millions of kilometers, a collision course was set, not with Earth, but with knowledge. This is the cosmos unfolding in real time. No predictions. No rehearsals. Just physics, pressure, and plasma. You don't get many of these. That's why the world is watching. That's why the data matters. Because for a few nights in October 2025, the sky became a laboratory, and Comet Swan, silent for so long, took center stage. Stay alert. Keep watching. And if you've got a telescope or even a clear horizon, you might just witness one of the most dramatic interactions of the solar cycle play out right above you. Science isn't always slow. Sometimes it races toward you with a tail of ionized gas and a storm at its back. This is one of those times. Subscribe now to stay ahead of the next cosmic event, from Earth-threatening solar flares to the rare arrival of interstellar travelers. Because out here, nothing waits, and neither should you. You wake up the next morning, and the comet's still there. But it's changed again. The tail is longer, sharper. There's a distortion in its structure, a kink that wasn't there yesterday. Observers across the globe are comparing images, frame by frame, hour by hour. And the data tells a story that words can't fully capture. Something has hit, or more precisely, interacted. The CME has reached Comet Swan's domain. Billions of tons of solar plasma, magnetically charged, moving at hundreds of kilometers per second, slamming through the ion-rich environment surrounding the comet. Not a direct hit, but close enough to disturb the balance, close enough to force change. The kink is real. So is the sudden drop in brightness near the base of the tail. You're not looking at a visual illusion. You're witnessing a magnetic reconnection event on a cosmic scale, where the sun's magnetic field ripped through the one shaped by Swan's own ion emissions. And in that split second, the tail snapped like a wire under tension. This is called a tail disconnection event, a literal tearing of magnetic field lines that were once continuous. Plasma doesn't behave like matter under normal conditions. It follows rules that don't make intuitive sense. And when these rules break, when the fields cross at incompatible angles, those lines don't bend. They break. Then they reconnect in a burst of released energy, and everything changes. It's violent. It's invisible to the eye. But it's there, in the structure, in the shifting alignment of ions, in the way the tail veers off course like a river abruptly rerouted by an unseen hand. This is how we learn. not by simulating plasma behavior on Earth, but by watching unfold where the environment is real, the scale is uncontrollable, and the physics obey no human design. And it's not done. The tail that disconnected isn't gone. It's still drifting, just no longer attached. A ghost appendage, still moving with momentum, but no longer fed by the core. That tail will fade, disperse, get shredded by the solar wind. Meanwhile, a new tail begins to form, already growing behind the nucleus, driven by fresh outgassing and a rebalanced magnetic sheath. And Swan keeps flying. But it's not the same comet anymore. Not structurally, not magnetically, maybe not even internally. The interaction could have triggered more fracturing inside the nucleus. That's not speculation. It's physics. When the magnetic field around a comet collapses and reforms, it changes how ionized gases are expelled. That can affect the pressure inside the body, sometimes catastrophically. What happens next? You wait, you observe, because no two comets behave the same way under stress. Some stabilize, some explode. Now multiply this by the proximity of the interstellar object 3 I/Atlas. Atlas didn't flare. It didn't outburst. Its brightness curve remained mostly stable. But even in the absence of visual drama, the comparison is stark. Swan responded to the sun with volatility, with energy, with chaos. Atlas didn't. Different origins, different materials, different thresholds for stress. And that difference is data. That's why these alignments matter. Not for symmetry, for contrast. Every element of this event, Swan's tail disconnection, Atlas's relative calm, the timing of the CME, has become a live demonstration of the way celestial bodies behave under solar pressure. For astrophysics, this is not a curiosity. This is gold. And people on the ground are the reason we're able to watch it unfold with such clarity. Amateur astronomers in over 50 countries have submitted time-lapsed imagery, polarization data, tail orientation measurements. That's not supplemental data. That's mission-critical intelligence. Because professional observatories have limits, gaps in coverage, restricted schedules. But the sky is always overhead somewhere. And the collective eye of the world has made this event visible from every angle. The global response to this comet has turned it into one of the most crowdsourced cosmic events of the decade, and it's changed how we understand space observation, not as a top-down model, but as a collaborative network, distributed, continuous, resilient. This is the future of celestial tracking. But Swan isn't finished. The outburst that started all this wasn't just a flare-up. It was a warning sign. When a comet brightens that rapidly, when its tail expands that far, that fast, it's a red flag for internal instability. And the added stress of the CME, combined with ongoing solar radiation, means there's still a very real chance of fragmentation. That would be the final phase. Core failure, a breakup event, the nucleus cracking into smaller bodies, each carrying its own momentum, its own arc, its own signature. We've seen it before. Comet Ison in 2013. Sun grazers that disintegrate under solar proximity. Bodies like Shoemaker-Levy 9, torn apart by gravitational forces before slamming into Jupiter. And while Swan isn't headed for the sun or a planet, the forces acting upon it are real and growing. The sun isn't calming down. Solar activity is ramping up. Cycle 25 is just getting started. More flares, more CMEs, more unpredictable space weather. And comets like Swan are the canaries in that cosmic coal mine, reacting to changes long before they reach us. Their tails are sensors. Their structures are test beds. They respond to the forces we can't yet measure in real time. That's what makes this more than spectacle. This is a forecast. If you can see how Swan breaks apart under solar pressure, you can understand how other objects, maybe closer to Earth, might respond too. Whether it's an asteroid in an unstable orbit, or a comet on a more threatening trajectory, or even satellites and space stations caught in the wrong place at the wrong time during a solar storm. This isn't a drill. This is training. And it's happening now. The scientific implications stretch far beyond a single object, from the dynamics of cometary outbursts to the geomagnetic consequences of CME tail interactions. Every frame of data we capture from Swan feeds into a broader understanding of how the solar system functions under pressure, and it changes how we plan, how we build shielding, how we monitor deep space, how we design missions to visit or redirect small bodies. Because you never know when a passive, distant comet becomes an active, high-stakes anomaly, brightening overnight, reacting violently, and giving us just a few days to witness something that hasn't happened in decades. Our 2 Swan was not on anyone's watch list. Now it's center stage. And it's still moving. Its tail, reshaped by magnetic war, now trails behind it with less symmetry, but more information. Its core, potentially unstable, continues to spew ionized gas into space. And its place in the sky, juxtaposed with an object from another star system, gives context we can't manufacture. We're watching the solar system react to itself, and to an outsider. This is what the universe does when we're not watching. And this time we are, because when you zoom out far enough, this isn't just about Swan. It's about every force that governs our place in the cosmos. Gravity, radiation, magnetism, ionization, and time. We see a tail snap, and we're watching magnetic reconnection in action. We see 2 comets take different paths through the same energy field, and we're watching chemical and structural diversity under pressure. We see citizen scientists align their observations with professionals across continents, and we're watching a new model of discovery unfold. This moment won't last. The comet will fade. The data will be processed. The tail will dissipate. But what it leaves behind is permanent. In models, in memory, in the architecture of the next mission that goes out to study these strange, reactive, high-velocity objects. Because they're not just debris. They're messengers, carrying information from the birth of the solar system, or from somewhere else entirely. And when they pass close, when they flare up, when they break apart, they're giving us one chance to listen. Comet R2 Swan has spoken. Subscribe now to stay locked onto the sky's unfolding chaos. From solar flares to space weather storms, from interstellar wanderers to ancient cosmic messengers. Because when the universe decides to speak, you don't get a second opportunity to hear it.